Hello students, I am Professor NAVNEET from EC Department SIRT Bhopal. Today I am taking lecture on subject digital communication. The topic which I will be teaching here will be Fourier transform of periodic signal. Now first we will see the difference between the analog and digital signals, continuous time and discrete time signal. Here in this slide, we can see the first figure which represents a signal which is analog as well as continuous time in nature. The signal is analog signal because it can have infinite number of values along the y-axis. It doesn't have fixed levels along the y-axis. Further, the signal is defined at every instant of time. Therefore, the signal is continuous time signal. Now, in second figure, figure number B, we can see the signal is defined for a fixed levels along the y-axis. It can have two distinct levels along the y-axis. Therefore, the signal is digital in nature. As well as the signal is continuous time because it is defined at every instant of time. Whereas in figure C, we can see that the signal is defined at only discrete instance of time. Therefore, the signal is discrete time signal. Whereas along the y-axis, it doesn't have the fixed levels. It can have infinite number of values along the y-axis. Therefore, the signal is analog in nature. And in figure D, we can see the signal is digital as well as discrete time signal. The signal is digital in nature because it is having two fixed levels along the y-axis, and it is defined at discrete instance of time. Therefore, the signal is discrete time signal. Now, in this part, we will see the Fourier transform of a periodic signal. Till now, we know that the periodic signal is defined by Fourier series whenever we want to analyze its spectrum. But here we can see that the Fourier transform can also be used as a tool for analyzing the periodic signal in frequency domain. Now we'll start with the signal ft, which is periodic in nature and it is having fundamental period t. Now, since the signal is periodic in nature, it can be represented by exponential Fourier series, which is given by the expression summation n is equal to minus infinity to infinity fn e to the power jn omega naught t, where fn is known as Fourier series coefficient and omega naught is given by 2 pi by t, where t is the period of the periodic signal. Here n is the integer value. Now, we will take Fourier transform on both the sides of this equation. So, Fourier transform of ft is equal to Fourier transform of this expression which is given in the summation. Now, I will rewrite this expression. So, summation fn Fourier transform of e to the power jn omega naught t. Now, for convenience, I have written it as 1 into e to the power jn omega naught t. Now, we have already done frequency shifting theorem. In the frequency shifting theorem, if we are having any signal ft, which is having Fourier transform f omega. Now, if ft will be represented by exponential in frequency domain, the Fourier transform will be shifted by the same frequency which is represented in the exponential. Now, here we can see that here the fundamental signal is 1 and it is multiplied by the exponential function e to the power jn omega naught t. Now, we already know that the 1 is having Fourier transform 2 pi delta omega. Now, when 1 is multiplied by e to the power jn omega naught t, in this case, using frequency shifting theorem, the Fourier transform will be shifted by the frequency n omega naught. So, here we can see that the Fourier transform of 1 into e to the power jn omega naught t will be given by 2 pi delta omega minus n omega naught. Now, we will put the value of f Fourier transform of e to the power jn omega naught t from here in this expression. So, here we will see Fourier transform of ft will be given by summation n is equal to minus infinity to infinity fn and the Fourier transform of this value, which will be given by the expression 2 pi. 2 pi is taken outside because it is independent of n, and delta omega minus n omega naught. So here we can see that the Fourier transform of a periodic function, it consists of a train of equally spaced impulses. Now we will explain this concept by using an example. Here in this example, it is asked that find the Fourier transform of signal consisting of sequence of equidistant impulses. Now here in time domain, we have sequence of impulses which are separated by interval capital T from each other. So we have represent this signal by delta subscript T, and parameter is T. Now here it is a series of impulses, and in subscript capital T is given because the time period of this signal is capital T. Now I want to find out Fourier transform of this periodic signal delta T. Now this periodic signal can be represented by series of impulses where impulses are located at t is equal to 0, t is equal to capital T, t is equal to capital 2t, t is equal to minus t, t is equal to minus 2t, and so on. So this delta tt can be represented by delta t plus delta t minus t plus delta t minus 2t till delta t minus nt. Similarly, for negative side, delta t plus delta t plus 2t till delta t plus nt. Now, using the formula for Fourier transform of periodic signal here, we can see that we have to find out Fourier series coefficient, which is Fn. So first, in the given example, we will find out the Fourier series expression, Fourier series coefficient, which is Fn. Fn is given by the formula 1 upon time period t, integration over 1 period, which is minus t by 2 to plus t by 2, and the signal which has to be analyzed, which is delta tt in this example, and e to the power minus jn omega naught t dt. Now I have to consider this signal in one time period, which is minus t by 2 to plus t by 2. Now here in this figure we can see that by taking this signal in between the period minus t by 2 to plus t by 2, it is defined by only one impulse, which is located by small t is equal to 0, so which is represented by delta t. So in this integration, for this period, the signal will be represented by delta t, and the rest of the expression will remain same, e to the power minus j omega naught t, integration between minus t by 2 to plus t by t, and 1 upon t. Now we will solve this integral. Now, using the sampling property of unit impulse function, we know that when an impulse function is multiplied by any other time dependent function, then the impulse function will remain same, whereas the other time dependent function will be defined at the value of small t at which this impulse function is located. Now we can see that this impulse function is located at small t is equal to 0. Therefore, this exponential will be defined as small t is equal to 0. Now, if I'll consider e to the power minus jn omega naught, and for this t I'll take 0, it will be e raised to power 0, which will give you value 1. Now I'll be left with only minus t by 2 to plus t by 2 integral of delta t t. We know that the area under the unit of impulse function is 1, so the value of this integral will be 1. So the value of Fourier series coefficient will be 1 by t. Now, taking this value of 1 by t, I'll substitute the value of Fn here in this expression. So, the Fourier transform will be 2 pi summation 1 upon t delta omega minus n omega naught. Here we can see in this 2 pi 1 upon t delta omega minus n omega naught. Now we know 2 pi by capital T is given by omega naught. So summation rest of the expression will be written as delta omega minus n omega naught, where n is equal to minus infinity to plus infinity. So here we can see that in frequency domain, again we get a series of impulses which are separated by omega naught, and each impulse is having amplitude omega naught. Now, thank you so much. This is all for the today's lesson.